Welcome you all. Today we are going to discuss about one more problem in fuels and combustion. It said that a four-stroke engine is running on methane with an equivalent ratio of 0.8. The air and fuel enter the engine at 25 degrees centigrade. The exhaust is at 527 degrees centigrade. And the heat rejected to the coolant is 340 megajoule per kilomole of fuel. Write the equations of stoichiometric combustion and actual combustion. Second one, by calculating the enthalpy of exhaust flow, deduce the specific work output of an engine and thus overall efficiency. If the engine has swept volume of 5 liters and a volumetric efficiency of 72% based on the airflow, calculate the power output at a speed of 1500 rpm. The ambient pressure is 1 bar. They given that engine is 4-stroke, fuel is methane, equivalent ratio is equal to 0.8, inlet temperature 25 degrees centigrade, exhaust temperature 527 degrees centigrade, heat rejected to the coolant 340 megajoule per kilomole of fuel. First we have to write this inlet temperature is equal to 298 Kelvin, exhaust temperature is equal to 800 Kelvin. Find it, write the equation of stoichiometric combustion and the actual combustion. Second one, by calculating the enthalpy of exhaust flow, deduce the specific work output of an engine and thus overall efficiency. Third one, if the engine has swept volume of 5 liters and volumetric efficiency of 72% based upon the airflow, calculate the power output at a speed of 1500 rpm. Here, this is the engine, the reactant at 298 Kelvin, where what are the reactants? Fuel plus air. It will be producing a work. Engine is supposed to produce a work. The products are at 800 Kelvin. These products are CO2, H2O, N2 and O2. In addition to that, what they given heat rejected 340 megajoule per kilomole of fuel. Assume that the combustion is complete and the calorific value of methane is equal to 802.64 megajoule per kilomole of fuel. The first one is stoichiometric combustion equation. We know that the stoichiometric combustion equation, methane, it will be reacted with n amount of O2 plus 3.76 amount of N2, that is for air, to produce A amount of CO2, B amount of H2O, C amount of N2. First we have to find out how much the air required for complete combustion. We know that for any fuel which has a molecular formula CaHbNCOD, stoichiometric air fuel ratio is equal to A plus B by 4 minus D by 2. In this case, methane is CH4, stoichiometric air fuel ratio is equal to 1 plus 4 by 4 minus 0, that is equal to 2. So 1 kilomole of methane reacted with 2 kilomole of air to produces 1 kilomole of CO2, 2 kilomole of water vapor and 2 into 3.76 kilomole of nitrogen. They given that equivalent ratio is equal to 0.8. What the equivalent ratio is the ratio of stoichiometric air fuel ratio over the actual air fuel ratio. Now this equivalent ratio is equal to 0.8, stoichiometric air fuel ratio is equal to 2, the actual air fuel ratio is equal to 2 divided by 0.8, that is equal to 2.5. So that the combustion equation becomes 1 kilomole of methane reacted with 2.5 kilomole of air produces 1 kilomole of CO2, 2 kilomole of H2O and 9.4 kilomole of N2. Some amount of oxygen present in the exhaust due to the excess air supplied. How much excess air supplied is the actual air fuel ratio is equal to 2.5 minus stoichiometric air fuel ratio 2. Therefore, 0.5 oxygen will be present in the exhaust. This is the actual combustion equation. The second question is specific work output and overall efficiency. Now, write down the engine free body diagram. The fuel and the air enter to the engine as reactant at temperature of 298 Kelvin. It will be producing work W and leaving the products at 800 Kelvin. These products are CO2, H2O, N2 and O2. In addition, there is a heat rejection to the coolant is 340 megajoule per kilomole. When you are writing steady flow energy equation, we can write that enthalpy of the reactant, that is inlet, is equal to work plus enthalpy of the product plus heat rejected. Now this work is equal to enthalpy of the reactant minus enthalpy of the product minus heat rejected to the surrounding. We can take it as equation 1. The first term, enthalpy of the reactant is equal to HR is equal to enthalpy of 1 kilomole of methane plus 2.5 multiplied by 1 plus 3.76 kilomole of enthalpy of air at 298. From the thermodynamic table, the enthalpy of methane is equal to minus 74.520 plus 2.5 multiplied by 4.76 multiplied by enthalpy of air at 298 is equal to 0. We can say that enthalpy of reactant is equal to minus 74.520 megajoule per kilomole of fuel. This is equation 2. Now enthalpy of the product is equal to 1 kilomole of enthalpy of CO2 plus 2 kilomole of enthalpy of H2O plus 9.4 kilomole of enthalpy of N2 plus 0.5 kilomole of enthalpy of O2. From the thermodynamic table, we can find the enthalpy of carbon dioxide is minus 370.699 and the enthalpy of water vapor is equal to minus 223.831. Enthalpy of nitrogen is equal to 15.042. Enthalpy of O2 is equal to 15.837. That is equal to 1 into minus 370.699 plus 2 into minus 233.831 plus 9.4 into 15.042 plus 0.5 into 15.837. While simplifying this one, we can get minus 669.047 megajoule per kilomole of fuel. This is equation 3. Now substituting this equation 2, 3 and heat rejected, we can find work output is equal to minus 74.520 minus of minus 669.047 plus minus 340. We can get 254.52 megajoule per kilomole of fuel. Now the overall efficiency is equal to the work output divided by heat supplied. We know that this work output in terms of kilomole, so the work output is equal to 254.52 over the calorific value. Already we assume that 802.64. It will be producing 31.71%. So the second part is over. The third one is the power output of the engine. The power output of the engine is equal to mass flow rate multiplied by work flow rate. Work output. This mass flow rate is in terms of molar flow rate multiplied by work output. The work output we already derived from the previous question. Now this molar flow rate. This molar flow rate can be derived from PV is equal to N into R naught multiplied by T, so that we can find out PV over R naught T. Then this V is the volume of the fuel. This volume of the fuel can be identified from the air fuel ratio is equal to mass of air over the mass of the fuel, that is equal to volume of air over the volume of fuel. This volume of fuel is equal to volume of air over the air fuel ratio. Now the unknown term is volume of air, that we can be derived from, we know that volumetric efficiency is equal to the volume of air over volume equivalent to the sub volume, that is volume of air is equal to volumetric efficiency multiplied by sub volume multiplied by this N star can be written N by 2 for 4-stroke engine. To convert RPM into revolution per second divided by 60. So this volume of air, volumetric efficiency they are given 0.72, then 5 into 10 to the power minus 3 meter cube, then the speed of the engine is 1500 RPM, 2 into 60. So we can get volume of air is equal to 0.045 meter cube per second. Then this volume of the fuel is equal to 0.045 over the air fuel ratio 2.5 multiplied by 1 plus 3.76, that is equal to 3.7815 multiplied by 10 to the power minus 3 meter cube per second. Then molar flow rate N is equal to PV divided by R naught into T. P is equal to 1 into 10 to the power 5 multiplied by 3.7815 into 10 to the power minus 3 over R naught is equal to 88314 multiplied by temperature 298. Upon simplification, we can get N is equal to 1.526 into 10 to the power minus 4 kilomoles of fuel per second. Then the power output is equal to N naught into W, that is equal to 1.526 10 to the power minus 4 multiplied by 254.52. We can get 0.03884 megawatt, that is equal to 38.84 kilowatt. The first question is combustion equation. The stoichiometric combustion air fuel ratio is equal to actual combustion air fuel ratio is equal to 2.5. The product of combustion in this case is CO2, H2O, N2. In this case, the product of combustion CO2, H2O and N2. In addition to that, there is O2. And the second question is the work output is equal to 254.52 megajoule per kilomole, and the overall efficiency is equal to 31.71. Then third question, the power output is equal to 38.84 kilowatt. Then additionally they are asking what will happen if the mixture is in rich, so that instead of producing O2 in the exhaust, it will produce that will take some part from the carbon dioxide.
Subscribe to our channel, like if you're satisfied, and share because it may be useful to someone.